So this is a telescoping sequences, or what is a telescoping sequence? So this sequence, it's just the sum as n equals 1 to infinity of this. So if we think about it, this becomes 5 over 1 times 3 plus 5 over 2 times 4 plus 5 over 3 times 5, etc., etc., etc. And we want to know whether this is a convergent series. And the telescoping sequence actually tells us what it converges to. Now, most of the time with telescopic sequences that I can see, we use partial fractions. Okay, so so usually with these telescopic sequences or series, whatever you want to call it, you have a fraction, it seems, and what we're looking at is we're looking at this as a partial fraction. So we write it as a partial fraction. So let's look at this as a partial fraction, and we're going to write it as a over n plus b over n plus 2. We know that this is true for some a and b. This is going to equal 5 over n outside of n plus 2. Why is that? Because if we get a common denominator, we're timesing the b by n plus a times this we're going to times this by a plus 2 over a plus 2. We're timesing this by n over n, and we get back to our denominator here. So we've got b times n plus a n plus 2a. And we know that that equals 5. Now, the only way that can equal 5 is if, well, you've got 2a equals 5 and b plus a n, well, that equals 0 because there's no n term up here. So this equals 0. What does that tell us? That tells us that a equals 2.5. And if a equals 2.5, b must be equal to minus 2.5. Okay? So what we're going to do is we instead of writing this series out like this, what we're going to write it out is like this. So instead of what we know is that the sum of n to infinity, from 1 to infinity, of 5 over n outside of n plus 2 is the same as the sum n equals 1 to infinity of 2.5 over n minus 2.5 over n plus 2. Okay, and we can take the 2.5s out, so it's just going to be 2.5 outside of the sum of this, the sum of 1 over n minus 1 over n plus 2, and this is still n equals 1 to infinity. Okay, so this is, if we wrote out this telescoping sequence, and this is why we call it a telescoping sequence, at n equals 1 we get 1 over 1 minus 1 over 3. And then n equals 2 we get a half minus a quarter, plus a third minus a fifth, plus a fourth minus a sixth, all the way up to plus maybe 1 over n minus 1 over n plus 2. And so what happens here is the nice thing about this telescoping sequence is that this 1/3 is going to cancel out with this 1/3. This minus a quarter is going to cancel out with this minus a quarter. This minus a fifth is going to cancel out with the plus a fifth up here. And what you're going to end up with is that 1 is not going to cancel out with anything. It's going to be obviously 2.5 times. This 1 isn't going to cancel out with anything. Plus a half is not going to cancel out with anything. And what are we going to be left with up at the other end is we're going to be left with if we think back a couple of terms here, it's going to be like 1 over n minus 2 plus this minus 1 over n minus 1, or plus 1, sorry. This is always 2 more than that. So this is n minus 2, this is n. Then it's plus 1 over n minus 1 plus, sorry, minus, he's having a nightmare, n plus 1 plus 1 over n minus 1 over n minus 2. So, plus 2. And again, what cancels out? Well, if you can read my writing, this will cancel out with this, and everything will cancel out except for the minus 1 over n plus 1, because nothing cancels out with that, and the minus 1 over n plus 2, nothing cancels out with that. Now, all of that, really, what happens to these terms as n approaches infinity? They approach, because I've lost my limits here, this is all the limit as n approaches infinity. So we really get 1.5 times 1.5, 2.5 times 1.5 minus 2.5 times something that is approaching infinity. So we just get 15 over 4, because this becomes irrelevant. Sort of muddled through that one a little bit. If we look at a second one, and we look at it in terms of a telescoping sequence, and we'll try this one. We want the limit as n equals 1 to infinity of the log of n plus 2 over n. Okay? So what does this look like? This is the limit, or the sum of the log of n plus 2 minus the log of n. Okay? As n equals 1 to infinity. So if we write out the sequence, it's always nice to write it out, I think. What you get is the log of 3 minus the log of 1 plus the log of 4 minus the log of 2 plus the log of 5 minus the log of 3. And I try to write out a few just so I can really see what's going on. Right the way up to plus, say, the log, let's see if I can get it right this time, n minus 1 minus the log of n plus 1, because it's always 2 less. Let's do, that's n plus 1, this would be n minus 1, plus the log of n plus 2 minus the log of n. So I've written a few out here. Remember these brackets, and if we want, we can put these in brackets. Now, in this case, what cancels out, we're going to have this log 3 is going to cancel out with this log 3. This log 4 plus log 4 minus log 4. And it's going to keep going. The next one's going to be log 5. The next one there is going to be log 5. So all of these are going to cancel out. This log 5 is going to cancel out with that. So what are we going to be left with? We're going to be left with minus the log of 1 minus the log of 2 plus the log of n plus 1. There's going to be nothing to cancel this one out, and there's going to be nothing to cancel this one out. So plus the log of n plus 2. Okay? So at the front, we're left with these ones, the back terms at the front. So at the end, we're left with the front terms, because there's nothing going to be cancelling out these front terms. Now, remember, this is the limit as n tends to infinity of this. This is a constant. This is a constant. These two things are approaching infinity, though, so this means that it is a divergent series. As I said, most of them deal with partial fractions. This one didn't deal with partial fractions because it basically didn't work. Okay, hopefully that's the telescoping sequences. Hopefully that explains it a little bit. Thanks. It's approaching on it. Yeah, I know that.